So why is it that data modeling and time series fit together? And I'm going to try to explain a little bit why. So, wake up. Here's some interesting facts, right? Well, I'm just going to establish my use, why I want to talk about this. So the Internet of Things is very interesting new development. It's kind of like, it's almost getting to be like a cloud buzzword now. IoT. Was that IoT? Yes, it is. But I think it's pretty real. It's whatever we define it as, regardless of what buzzword it is, whatever some analyst says there's a gazillion-dollar market for, it still comes down to one thing. We're attaching things to the internet really quickly. You guys know what that thing is up there? This right here? That's a Nest. You know, it's funny, I said that in Europe, and everyone was like, thermostat? But it's a Nest, right? Google just bought Nest for $3 billion. Now, do you think Google was in a board meeting and they're like, man, you know, we got this cool self-driving car, great search engine, got Google Apps, that's cool. You know what we need? A thermostat. No, they didn't say that. What they said is, man, I have like one in my house, do you? Yeah, I do. Dude, it knows when we're here. We need that data. That's what they bought. They bought $3 billion of what the F you're doing. You know what's creepy? I have Nest. It knows when I'm there. It knows when I leave. It knows what temperature I like. Google wants that information. Ergo, NSA has it now. I did this in Europe. It was really a fun trick thing. I changed the temperature of my house. It's currently 64 degrees in my house. I'll change the temperature if I want. How cool is that? And then that's what this is, this Internet of Things. Now, did I ever mention once when I talk about Nest, the Internet of Things? No. But it's a cool product. It's a cool thing. It is moving fast. CES in January, refrigerators talking to the internet, telling your grocery store you're out of milk. These are all just things that goes in the future, right? And your car now talks to its sink. So all these devices are going to be talking. So 15 billion devices by 2015. I think that's a conservative estimate. How about 40 billion devices by 2020? That's a lot of mouths to feed. And all that means pretty much one thing. This all has to go in a database somewhere. So let's talk about what that is. And it's almost always going to be time series data, temporal data. Here's something that happened at this time. Cassandra's a great home for that. And it wasn't really designed for that initially. But why Cassandra for time series? And then I'm going to use this as a data modeling launching point. So, as you saw in my last talk, one slide proved it all. And if you're not a Cassandra user, you can prove it to yourself. But Cassandra scales. That's a good thing for your IoT, because there's going to be a lot of them apparently. It's resilient, which means that it's going to be online all the time, and it's going to deal with all the crap that I throw at it. It's great data model. Aha! Let's talk about that. That's going to be a big part of this. But then beyond that, and this is the kind of the secret sauce of Cassandra of why time series data is so good, is this efficient storage model. Now the efficient storage model, as a programmer, I really don't care too much about, right? That's not something I'm going to concern myself with as I'm writing code. But I want you to understand what's going on, just so when you're writing code and you're looking at the data model, you understand what's going on under the scene. Because let's face it, what about that? I mean, this is the power, what Cassandra could do. So let's start out with the data model example, because I like examples. Good old weather station, and classic, right? This is classic time series. Temperature over time. So I have a weather station here. I'm putting that data into a Cassandra ring, and I'm going to display it out in the whatever format is RD graphs, whatever. So over the whole day, I graph all the different data points. Great, right? So that's an easy one. So what do you start with Cassandra data model? Data modeling is a little different in Cassandra because what we're doing, instead of taking the data and then building models, we're taking our application and building the model. So I'm going to start out at the top with what's my application going to need for a query? The application is going to ask for this data. I'm going to graph this data on my website. What are those queries look like? So the first thing is I want to get, here are my needed queries. I want to get all my data for one weather station. Okay. I want to get all the data for a single date and time. And I want to get data for a range of date and times. So all very similar around the single weather station ID, weather station itself, but a little different. I want a single date and time. I want to get a range. So how do I model that? So my data models support these. It's pretty simple. I'm going to store data per weather station. That's my first requirement. My second requirement, I'm going to store in time series order, first event to the last event. So what does that look like? So I'm going to create a table. My create table is pretty simple. I have a weather station ID, which is just a text. I use text because it's, here's the actual value down here. It has some letters in it. Event time, which is a timestamp. So this is when it actually took the reading off the weather station. And then a temperature, text. Now the primary key is the interesting part here. This is what makes the data model rich. And I'm going to show you why it makes a difference in a minute. But this primary key is an important piece of your table creation. Because what you're specifying here is the uniqueness, that partition. The partition is, here's all my data that I would order in a certain way, and that are co-joined together. So much like how a relational database has a primary key that says these two combined, these two values are unique, same thing. But what this is also doing is changing the way I store my data. And I'll explain that. So here's the inserts. Look familiar, right? Insert into, and I have 1 minute, 2 minute, 3 minute, 4 minute. So every minute it's collecting data. It puts a time in there, or a temperature in there. Boom, Bob's your uncle, good to go. So whenever I do a select weather station ID and event time and temperature from temperature and my weather station ID equals this, whatever it's 1, 2, 3, 4, A, B, C, D, I get a table. That's exactly what I was hoping for, right? That's what I want. Now, if you look at the order of that data, again, I specified in the primary key the order of that data. So the order was, I want the first thing that happened to the last. Going back to this, the event time is that second part of the primary key. The first part sets up the partition. The partition is this weather station ID. Every element in that partition will be ordered by event time. That's how I would describe that to you. So yes, these two are unique. Weather station ID sets up the partition. Event time is the order that I want that partition in. So whenever I do a select off of this, I get everything in order without having to sort it in memory. Good? So what happens on the storage engine? I remember I told you, I teased you on that a little bit. The storage engine is the cool part of the story. Now, this is the part where, as a programmer, you may depart and say, well, I'm good with this. I'm moving on. I'm going to write my code and ship it because it's an agile thing, and I got to do a demo day tomorrow. But let's look and see what really happens, because I think this is the most interesting part. What's really happening on the storage engine is this. It actually lines up that partition in a single storage row. That partition, which is specified by 1, 2, 3, 4, A, B, C, D, is actually the beginning of a file. It's a file header. And then every record in a row sequentially on the disk are the elements in that partition. So what does this get you? Well, first of all, it's merged, it's sorted, and it's stored sequentially on the disk. Again, what does that get you? When I start adding data, it just appends it to the end of that record. That's great. So everything is still in order because it's merged, sorted, and sequential. This is great for storing data, but what's the point? Why are we doing this? The point is whenever I do something like this. Now this is my query where I'm going to ask for that range of time. Again, keep in mind that that was one of my application requirements. Is that when I query my data, I want to be able to grab a range of time. In this case, I wanted to grab it from 1 minute to the 4 minute. Not a very exciting time period, but that's what I want. This is called a slice query or range query. If you notice that it's the greater than or equal to, less than or equal to, this sets up these boundaries. What does this mean based on how I store the data? First of all, get a single seek on the disk. Unfortunately, Al's right next door telling you why disks suck. If you were to be over there and here at the same time, you're a freak, but that's cool. But you would hear him say, well, here's the problem. You're going to be running into disk problems. I'm going to tell you, yes, you're going to run into disk problems, trust me. But the way to get around some of those issues is to minimize the amount of seeks you do on disk. A seek on a disk hurts because let's look at everything in your computer. You know, the CPU is in nanoseconds. You know, memory is in micro or even nanoseconds now. But what does the disk do? Spinning is Rust. Milliseconds. Yeah. And that's like orders of magnitude slower. And we haven't really fixed that problem. Sort of. I mean, we have new disk technologies that are now available, but we still look at most disk storage systems in production right now are spinning Rust, and they're measured in milliseconds. If you're using a SATA disk, 7,200 RPM SATA disk, you're looking at 10 milliseconds of seek time, potentially. Hey, my query just turned into a 10 millisecond query just based on that one thing. And if I'm chasing milliseconds, that's going to hurt. Okay, so getting less than that one seek, or even less than one seek, you can do that, but getting less seeks is a good thing. So that single seek on disk, that's what I want. I want to put the disk head right at the beginning of my data, and because what I'm trying to do here is get this range, I'm going to grab all this data right here. And whenever I ask Cassandra to get it, it'll move the disk there and sweep across the head, and woof, puts it right back into a CQL table for me. Programmer sees this. They like this. So this is what makes that data model really efficient. Because it's stored on the disk, when you do a seek for that data, it's really fast. It's very efficient. You know, when I ran Oracle, the game was all about IOPS, right? Because why? Everything's random. All the I/O is random on Oracle, or on MySQL, or any relational database. You have a DB file, and it randomly reads and writes to that file. So you better have a lot of IOPS, because that means that you can do a lot of seeks and maneuvers around. Cassandra doesn't do that. Cassandra writes out those SS tables one time. Once. It never does a random write, ever. Yes?
How about like temperature?
If you what?
Like temperature.
If you want order by temperature.
That's a different data model. Right now we're just ordering, because I've specified the data model is I only want to order by date. I can specify an order by in this query, but that's going to have to get sorted in memory. My data model said I need to do a date slice. If I wanted to do temperature, I could change the data model around a bit there.
But if we follow up on that for just a second without taking too far. In Oracle, what you do is you create an index on that and you'd have a covered query. So that your temperatures would already be sorted. Yes, you'd have to go to the disk, but again, one seek, one read, it would all be clustered, and so you get all the data together.
Well, you'd use a group by, or you can order by. But if you create an index on a second field inside Oracle, it's not going to order it. It'll only make it more accessible. So when you run the query plan optimizer, it will find that data faster, but it's still not sorted on disk, and it still has to do a random read on disk. You're
No,
still
but the
stuck.
indexes are sorted. If you can do a covered query, it's all sorted, it's ready to go.
But the data isn't. That's my point. The data isn't, is my
Well,
point.
but you don't touch the data, you read it right out of the index.
You're going to read it out of the index, but when you want that data, you're going to do a random read. A lot of them. Because you're going to be putting these all in rows.
Only if you index one specific column, you only pull in that column. If you pull in extra columns in that table, you have clustering factors and fun stuff to do with it.
I've done this data model, similar ones on Oracle, and you will limit out real fast. And mainly because you run out of items. Sequential operations are going to be faster on larger data sets, and the bigger the data sets you have. I have one other reason this is going to be faster as well, and that's because you're going to distribute that many queries. So let's hold off on the questions for a minute. Let me move on to the next topic, and maybe that'll answer some of these questions. But it's not just about this one thing. There's a lot more to this. I got more secrets. So what about some additional help on the storage engine? So let me show you what the read path looks like on Cassandra in a nutshell. When a client asks for data, it goes to the key cache. The key cache is like, hey, I have that first part of my primary key. Where is that on the disk? I want to know where that is on the disk. If the key cache does a hit, you get the one data file hit, you do one seek, you're done. It's because your total seek time is going to be the disk latency times the number of seeks, right? And we want to try to minimize that. And we can measure all this in Cassandra, by the way. There is a tool called CF histograms, which I did a talk about. You can Google my name and you can find lots of my talks. But I did a talk about this thing called CF histograms. You can watch every single read and see how many seeks it takes to do this. This is a very important tuning technique if you're trying to get below a millisecond on every query. And I did that many times. 500 microseconds, 95th percentile is very doable if you do this right. So the next place is a Bloom filter. I talked about that in my last talk. Bloom filters are just a probabilistic function, and all they do is they say where the data is not. So again, we're trying to find out where the data isn't. If you have 1,000 tables to look at, I'd really like to narrow that down to a couple if I can. So the Bloom filter is yet another way to get that. So those two things in conjunction will help get us closer to that minimum number of seeks. But that's not always going to work out, because in cases where maybe that row of data, all my weather data, is spanning over 2 or 3 column families or 2 SS tables, I'm still going to do a lot of seeks. So the key to the speed in Cassandra, based on that particular read model, and how the reads work in Cassandra, here's the keys to speed. And this is important point number 1. The first part of the primary key, that first part, the weather station ID, gives you location. That's going to put you on a single server. And I'm going to explain how that works in a second. But that's going to put you on a single server. So if you have a 1,000 node cluster, that first part will put you on one of those servers in that 1,000 node cluster. It will not be a random seek. The second part, that partition key, will get you closer to the SS table. And you get it right, you want to minimize that seek. You want to get into that file as soon as you can. You want to minimize how much your disk is doing. And then the third thing, which I'm putting up here just for brevity, but we won't cover as much. I do a lot of performance tuning type talks. But the other thing is how fast you can find that data in the SS table. If you have a 3 gig file, you can use indexes to find that data immediately. So once you do a seek, you go to where the data is instead of having to move the diskette across the disk. So there's a new feature as of 2.0 that will help you get to that data faster. And this is actually there for time series data. And in those cases where I might have 3 files on the file system that could potentially have my data, I want to minimize how many seeks I have on the disk. So the same query, I have this, I'm looking for data in between 1 and 4. I know there's a bug in my code. I forgot to put an equals on there. I get pointed out often. Sharp crowd. But here's 3 files that it could potentially be in. Now this min-max hint, what we do is when we create those files now, we create an index. An index built on top of that file that says, hey, here's the minimum and maximum values for this primary key that you've set up in your data model. And you can use that later. So how does that used? So the minimum event time here is the index shows that it was March 27th to 31st. This one was April 1st to 4th, and this one was April 5th to the 9th. That's the event time. So if I look at my range over here, when I ask that question, it's like, hey, I would like a slice of that data, please. Cut me off a piece of that pie. I have 3 choices now before 2.0, which means I'm going to have to do 3 seeks to find that data, just to make sure that I got it, right? Well, with this index hint, now I'm like, well, that data fits in here. This is the file. 1 seek now. Time series data really can take advantage of this. There are other data models. It's not just for time series data that it works for, but this right here is how you get to that file fast. This is how I do time series data models in less than a millisecond. And that's, hey, IoT, when I'm messing around with my Nest, by the way, Nest uses Cassandra. I want to make sure I'm changing the temperature of my house and pissing off my wife really fast. I don't want to wait. So I'm going to change the temperature really quick. funny story about this. Little vignette. Our co-founder, Matt File, he has a Nest, and he had a roommate, Mike Blumen, who runs the Ops Center team. And when Matt was on the road at night, he'd jack up the temperature. Mike would wake up sweating. Oh, this is so hot in here. What's going on? Oh, the thermometer or the thermostat's broken. So what did he do? He called support. Hey, this thing's broken. So like, oh man, that's terrible. So they're all trying to diagnose it. They're running all these things on there trying to figure it out. They got back to him on an email. I think we found a bug. Here, apply this patch, do all this stuff. And finally found out that Matt was the one turning up the temperature randomly. The guys at Nest found out. It wasn't pretty. But anyway. Just keep in mind, you'll get busted eventually. I thought that was kind of fun. So now I can't do it anymore. So whenever I go to Nest, and now they're like, oh, say hi to Matt for us. He made us do all that extra work. So I want to, real quick, I want to go through some ingestion models right now about getting that data in there, because this is the next question I always get. If you're at the point where you have a database that can do millions of writes per second, you got to have an application that can do millions of writes per second. This is not a trivial problem. So one of the things that I like to point out is some of the methods you can get that in there, because this is this is a new game, right? When you're talking about Internet of Things, you need to get a lot of data in there. So one I hear so much about right now, and man, this is like Kafka this, Kafka that. Kafka was a project at LinkedIn who graduated him, grew up into the big world, and went to Apache. Now it's a top-level project. It's based on Scala, cool queuing system. It is based basically on the same type of paradigm that Cassandra is horizontal scaling. You add more nodes, get more scale. Lots of people using this now. And it's a really cool project, but I see it in conjunction with a few things. Storm is the other one. Storm is a processing framework. So if you're taking in a lot of stuff, refrigerators all around the world telling you what temperature it is inside the refrigerator, going through Kafka, making sure that gets once and only once delivery. Storm will then roll it up and do different things with that data. You've got a lot of data coming in. What are you going to do with it? You need a database that can scale up. Cassandra seems to be the place people put that data. Another one is one of my projects, Flume. I was recently at the Hadoop Summit, which is kind of funny for a Cassandra person. And one of the guys in my talk was Jonathan Shea, who was the original author of Flume. And as I'm talking about Flume, I see this guy like smiling in the back. I'm like, oh. I used to work on this project. So it was kind of cool seeing that back in middle school. This is an old project, actually. It's a few years, about 4 or 5 years old. And it was originally built for ingesting logs. I used it for bringing in syslog events. But it's a very simple program. You create a source with a listener, like syslog, HTTP. There's a channel, which is like a bus, and then the sink, which picks up those events off the channel, and then you can do transforms. What I did is I built a system that basically took in HTTP events from our F5 load balancers, and it parsed out the entire web log string, and then created 90 different inserts based on that one web hit. So I created this massive web amplifier, right? And it was the only thing I was trying to put it into an Oracle database. It failed, and then I just ran out of money, really. I tried to do it, and the only thing that really could scale up was Exadata, and I didn't feel like spending $2 million on this one little log processing thing. So I started using Cassandra. That was when I first started it, and that was on 0.7, and it just worked. So I noticed that this thing is producing tons of data. I couldn't do anything with it. The only other choice is I could dump it into S3. And then what are you going to do with it? That doesn't mean anything. I needed that data in milliseconds, so Cassandra was my choice. So let's talk about that data with speed, and this is going to move us into a different data modeling topic. So if you're going to do 1 million writes per second, do the math. That's an insert every millisecond, or microsecond. Microsecond. That's fast. I don't know about you, but I don't know a lot of applications that could deal with that too much. You've got to work as a team if you're going to do it with microseconds, right? And everyone's got to pitch in. If you put that on one single server, that is going to be the best microsecond you ever saw, and that thing's going to fail. So there's another problem is collisions. These are real problems. If you're in time series data, collisions are an issue. I did a talk at ING recently, the big bank, and they're pretty public. They're doing financial transactions using Cassandra. And they're also very public about the fact that there could be potential collisions and how they manage it. They'll be doing a really cool talk at our summit in a few months. So, this is a problem to deal with, right? Are you next?
I'm just looking for
You can
some.
set up. So how do we manage that much data flying in at the speed of microsecond? So the first thing is primary key, placing it in that node placement. And I'm going to teach you how that works, because I think you need to know that. Programmers, architects, this is how data gets distributed, but it's also how you can do a lot of things, and how your data model really depends on making that right. Also, the random partitioning, how your data gets spread around, that's a part of Cassandra. And then we also have a special data type called a time UUID. A time UUID is a great tool for avoiding collisions with time series data. So let's talk about what happens with our weather stations. I got a lot of weather stations to feed. So let's quickly go into the replication story of Cassandra and how that relates to your data model. So the primary key, that first part of the primary key that I told you about, that is the important piece of figuring out what server it belongs to. So how do we do that? So we have this really basic data model. Our primary key is the first name of people, which is really a poor primary key, but for our limited data model, it'll work. So we have Jim, Carol, Johnny, and Susie. That's our data points. What we do in Cassandra with that primary key is we hash it. MD5 or murmur. That is a consistent hashing operation, so that if you put in the same string, you'll get the same 128-bit number out. Awesome. And this is how many technologies work. If you look at Memcache that far back, that's how it got data distributed in a reliable way. It was using MD5. It would hash it and then throw it out into a reliable way. So all these keys are hashed. Now, how does that do with Cassandra in this regard? And this is what I'm talking about, the data locality. Like, where is that data in relation to the physical layout of your server? How does it find it? So we have a 4-node cluster here, node A, B, C, and D. And each node will store a range of data, a range of tokens. So we take that big 128-bit number, which has a name I don't remember, like a septabyte or something, and we're going to break it into quarters. So this is 1/4 of the range on A, 1/4 of the range on B, 1/4 of the range on C, and 1/4 on D. Each one of those nodes now says, I'm primarily responsible for 1/4 of the range of that 120-bit number, meaning that when one of these is hashed, I will see if it fits inside my range, and then I'll own it, and no one else will take it. So I take Jim's number. Hey, it magically fits that 5e goes in between 4 and 8. Awesome. So now C is responsible for Jim's data. Carol, she goes to node D. Johnny goes to node A. Now, because MD5 is somewhat random, I know if you're a mathematician, I got grilled by a PhD in mathematics about, well, there's collision and it's not really random. Okay, but it's pretty random, and it's going to randomize the placement of that data around. So as the data is getting set in there, it's randomizing, so you're getting good distribution, but it's also going to different nodes. Now, what about the replication? Each one of those nodes can also say, you know what, because you're my neighbor, I'm going to hold your range too. So if I change my replication factor, that's all that means, is the nodes become responsible for its own data and then its neighbor's data. Maybe 2 neighbors' data, which is a lot better than my neighbor. My neighbor would never put anything of mine in his garage. But Cassandra is more like working like a team. So whenever Carol, which is the primary responsibility is D, well, A and B also say, you know, we'll hold that data for you as well. So it asynchronously replicates that data. It's not synchronous, asynchronous. It writes it at the exact same time. And it'll send it to 3 nodes at the exact same time. Now, the one missing part of this is consistency, which I'm not going to cover in this particular talk. But consistency is how the client knows that it got to those 3 nodes, or just 1 node. You pick. As a programmer, you can make a determination on consistency. And we just have to have Mr. Consistency here. Are you going to do the next talk here?
Mr. Inconsistent.
Oh, yes, you'll eventually be consistent.
Yes.
Christos from Netflix, he's going to do a talk on eventual consistency, which I think that will make you feel better.
We'll
right?
go into painful.
Painful consistency. Man. This is not painful right now. This is good right now. So this is how data gets replicated. Now, how does that fit in with the rest of it? Well, whenever I'm writing that million writes per second, if I have a very small cluster, 4 nodes, that means that there's a potential, that means that there's going to be a lot of writes per second per node. Now, that's because each one of them holds a quarter. So how does that linear scaling story work? If I double the amount of nodes, now each node is only responsible for one quarter, or 1/2 of the quarter, so 1/8. I had to do fraction math. I have an 11-year-old, so I'm doing a lot of this now. So each one of them is doing 1/8 of that data. If I double it again, then they're only doing a 16th, and so on. If I have 100 nodes, each one is worth 100th of that data set. So as you add more nodes, they're just responsible for less and less and less. That's how it scales out. Same with storage, same with writes per second. You're also spreading it around. With this replication factor of 3, if I have a 1,000 node cluster, it's still only going to replicate to 3 nodes, not to 1/3 or something like that. So that's how you keep those nodes, keep those writes spread out. So the time UUID, last topic here. So the time UUID is a timestamp to a microsecond, which is cool, that gets us part of the way there, plus a UUID. Now that UUID is added at the end in case you have the exact same timestamp. If you're putting data in your database like that, then you want to make sure these values are unique. That's the time UUID. So what's cool about these are also known as a version 1 UUID, which means it's somewhat of a standard. You can get there's support for it in Python and Java, that sort of thing. They're sortable, meaning that if you present a bunch of time UUIDs, they'll be in sorted order, and you could reverse it. So when you give it this, it'll go, I know what that is. That's this date. So you can figure out what day it is, or what the timestamp is based on this. This really, really super small link over here is a web page to make that, which I used on February 12th at 6:18 p.m. So here's my last example where we use that time UUID. So again, our data modeling, this is how we data model. My needed queries, I want to get all trades and symbol for it in a day. Christos, you're going to love this example, by the way. Get a trade for a single date and time, and then you get the last 10 trades. The last 10 trades. That's kind of a tricky one, right? How do I get the last 10? So my data model support that is I'm going to store my data per symbol and date. I'm going to store it time series in reverse order, last to first. And then I'm going to make sure that every single transaction is 100% unique. So even if they're the same microsecond. So I'm going to start buying some Netflix stock. A lot of it. I actually sold a lot too. So here's an interesting thing. I'm going to point out a couple of deals here on my data model. So these are just stock ticker data. Typical type of stock ticker data where it's coming in at a rapid pace. So there could be potentially some collisions. But what I've done here on my primary key is a couple of things. I put the symbol and date together as that's the location. That's my first part of my primary key. That's going to give me my locality. That's going to mean that for every date, which is just like for one day, and one symbol, it'll always go to the same group of servers throughout the day. So the next day it'll move to a different group of servers. And then the trade is a time UUID. So if I have the exact same, at the exact same second, microsecond, I'll still have uniqueness to that. And it'll be ordered. The last thing here is this clustering order by. This is a very fancy way of saying I'd like to reverse the order stored on disk by the trade, which is that time UUID. So that's kind of an interesting plan. So here's the order thing. I'm going to buy 2,000, I buy 300, sell 450, and sell 3,000. Okay, so that's the order that I did them in. When I go to look for that data, notice it's reverse. This is the last thing that happened at the top of the list. The first thing that happened is at the bottom of the list. So now I'm in reverse order based on the trade details or the trade time. That UUID gets parsed and reversed, but right now I can't even tell you what time it is. I'm sure you could. So what does this look like on the disk though, now that I've told it to reverse sort? This is when it gets really interesting. Because now what I did is because I told it to reverse sort and merge, now it actually does that on the disk too. So whenever I go look for that data, I'm going to say, hey, I want a limit of 3. Limit 3. Cool new terminology, or cool new syntax. What I'm saying when I say limit 3 is I only want 3 things returned, but because I know I reversed it, I'm going to get just 3 items. The last 3 items. The last 3 trades that happen. Boy, this data model is used so many places for fraud detection, for user sentiment, for identity tracking on websites. This is really a cool data model. So when I say limit 3, it's going to go to the beginning of the list. I didn't have to go all the way to the end and then come back. Go to the beginning of the list, from here to here, and just bring those rows back. Very efficient. Now, I just have the last 3 trades that have happened. I think that is a cool way to do things. Like I said, I've personally done a lot of these data models in production using a reverse, a clustering order by, with a limit to create really interesting interactions with time series. Because all those things flying in as fast as they are, you need to be able to do that. Yeah?
Is descending somehow slowing down your writes?
No, not at all.
How does it insert? Has to shift everything over?
Well, it's merge sorted in memory first. So it's a memory operation. And then that file, the way that the Cassandra writes out is a sequential write. So it'll write that file out. We're getting into like some operations things, but later, if there's 2 rows of data, it will do a compaction operation. That's a normal background operation. And then merge sort those in memory again. But that merge sort in memory, it's a hash map, will sort that properly. So it's not going to slow it down. Order is independent of how fast it can insert data. It's just the feature of how that works. Yeah, more questions? Because I'm at the end of my slides. So.
With the hashing, in order to distribute the workload on your cluster, how do you handle the imbalance?
There shouldn't be a lot of imbalance unless you specifically put it, well, with MD5, you're not going to get an imbalance.
I mean, if you're using a stock trading as an example for the data model, Netflix is a very volatile stock compared to the other one. So
right.
You would end up using the same node over and over again to write your data.
Potentially, yes. In those cases, and this is knowing your data model, if you know that's a potential case, here's a great example, is like if you're looking at URLs, all right, and you say, here's the row key is URL in a day, well, all day long, that row is going to be the hotspot. In that case, what I've done is I've put like a modulus in there or something else to make it more unique. And then had a consistent way of managing that. That's knowing your data model. But knowing what you just found out is pretty critical. Now you know, oh, if I do that, maybe that won't be so good. Maybe I will have a hotspot. I'll just be writing to the same nodes or the same replica set over and over again. Now what we hope for, like with the stock trade example, is there's a company called Circa that collects all stock trades around the world. 2 million a second. I doubt you're going to find a hotspot in that. Yeah, Netflix stock may be hot at one moment, but there's still a zillion other things going on. So it gets washed out in the noise. It may cause a little bit of a blip, but with that many writes per second going on in your cluster, that's not really a consideration. Now, if I was only looking at a select group of stocks and I knew that one was going to be way more than the other, okay, that's a different data model. So it's something you have to consider for sure. But if you look at the big picture, distribution of that won't be a problem.
I think another variation of the question, another concern is you're going to end up with some wide rows.
Right.
Is that a concern?
Not really. And the wide row concept, all right, so that partition, how big can a partition be? 2 billion cells. Now that's great, that sounds like a lot, but if I'm collecting like weather station data every second, it's not gonna last. That's when you get into too wide. Or if I just collect all trades for one stock, one symbol forever, then yeah, 2 billion is gonna get eaten up pretty quick. So that's when you probably want to think about, what am I doing in my data model? The reason I added date, that date in there, let's go back to this. The reason I added date in there is to eliminate that problem. Now that I know every single day will be a new day for a new partition that will have as many of that. Now, do I think I'm going to get 2 billion in a day? I'm saying no, I won't.
with this potential, with this data model, you would have potential problem at the time when the date changes. So if you're looking for limit 3 rows, and if there's not enough data and you have to spend across 2 different days.
What's great about the stock market? It's only open for 8 hours.
No.
You've got all this time to create that new table.
Yeah, no, and you're right. Maybe that's a different consideration.
Okay.
So, and that data model I showed you with the web hits, that actually had to deal with spamming. But what I did was, we just had a little bit of logic in our system where we could just grab both of those at those off moments. The chances that we did everything in UDT, the chances that everybody being at work at midnight UDT was pretty high. So that wasn't even an edge case for us. It was an absolute. But we just had enough code in there to deal with that one situation, and it was pretty efficient out here. So we didn't really have any problems with that, but it's something to consider, right? You're gonna be transitioning to a new partition.
Yeah, I think the point here seems to be is if you are designing a data model for this database, then you still have to think about all the edge cases before you design the model itself and how you want to justify.
A lot of times, yes. Yeah. And get to know data modeling. I put up here the Planet Cassandra. Oh, there's my animation again because I'm so proud of it. Planet Cassandra has a lot of cool interviews, those 5-minute interviews, like use cases, but also white papers, things like that. So I would hope you wouldn't have to reinvent a nice round wheel again. People like myself, I've done thousands of data models. And now I'm kind of like the horse whisperer. I just walk up and say, because I already get all the reasons we do things. And you'll get to that point too. I've worked with teams now for a long time. I've worked with Christos's team quite a bit. No one is really like digging too deep anymore because they get all the points and then they're just building the data models. And sometimes it's like relational. When I first started doing SQL, I'm like, what is this? This is crazy talk. But then after a while, I was just doing it in my sleep. It's the same way. But what I don't have to do now is think about how I'm going to scale this thing once it's in production. How I'm going to keep it online. How big my Oracle bill is going to be. So there. All right, we're out of time. It's 11 o'clock. Thank you very much.